Okay, in this video I'm going to be talking about multidimensional unconstrained optimization. So in previous videos I've talked about one-dimensional unconstrained optimization, so where we're looking for optima of functions of just one variable. So for example, we might have a function f of x that looks something like this, where it has a local optimum, a maximum value here, and we might want to know what that maximum is. So there's a couple of different ways we could do it. We could do it using calculus, so find max using calculus. And so to do that, we take the derivative of the function and set it equal to 0, and then solve for x. So that's the process if we're using calculus, or we could find the max using a numerical technique. Find the max numerically. And I introduced a method called the golden section search. Golden section search. And it's a bracketing method, so it's kind of related to the root methods there. You could also use root finding methods because you're looking for the root of the derivative, so other root finding methods also work. So other root finding methods such as bisection method, false position method, Newton's method, secant method, all of those methods you could use to find the root, possibly. Assuming that you know what the equation for f of x is, or for f prime of x. Now, what we're changing when we talk about multidimensional optimization is now we want to find extreme points, extrema, so maxes and mins of functions of more than one variable. So now what we're talking about is finding max and mins of functions of more than one variable. More than one variable. So for example, we might have some function f of xy, so a two-dimensional function, equals some equation. Maybe we have a parabola, so x minus a squared plus y minus b squared plus c. So this is a parabola that looks something like this. If I were to draw it in 3 dimensions, see how well I can draw this. So we've got x, we've got y, we've got b, we've got a. Here's their point right here, and then we've got c here, and this is f of xy, and this actually forms a three-dimensional surface, kind of like this, where you've got three-dimensional surface that looks like this. where now it's got kind of like a bowl shaped, and you have a min right here, and that min is found at f of a, b, and it's equal to c, because you see if you plug in a and b for x and y up here, these go to 0 and you're left over with c. So that's just an example of a two-dimensional function. So typically we're going to limit ourselves to functions that map from Rn, so some integer number n of real numbers, real variables, maps to R. Alright, so we're not limiting ourselves to just two variables. It could be we have a function of 7 variables, f of x1, comma, x2, comma, all the way out to x7. And that returns some scalar value, I could call it z. Alright, so and in this case I couldn't really draw that, but you can think of it as a high-dimensional surface. We can't draw more than two-dimensional surfaces, but you can kind of abstractly think about this as a hypersurface in which we're looking for max and mins. Alright, so the question is, how do we find maxes and mins of these higher dimensional functions, multidimensional functions? So, question, how do we find max and mins for multidimensional functions, for multi-dimensional functions? Well, there's always the calculus route, which is for one answer. So answer 1, you might say use calculus. So to do that, we're going to have to take the gradient. So take the gradient of our function and set that equal to 0. And now our gradient, the gradient of our function, del f, is going to be equal to a vector with the partial derivative of f with respect to the first variable, and then the partial derivative of f with respect to the second variable, all the way out till we get to the partial derivative of f with respect to the however many variables we have. So some vector that looks like this. So when we set this equal to 0, we're literally taking whatever equations pop out for each of these components and setting them equal to 0 and solving it. So we'll have n equations, n equations with n unknowns. And the equations can be nonlinear. The equations can be nonlinear. So I did a video a while back on solving linear and nonlinear sets of equations. All of those methods can be applied to solve this problem here. And in fact, that is an approach that we're going to take. So another very common method. So if we back up to this question here, how do we find max and mins for multidimensional functions? So calculus, solving by hand, we can do that for a few functions, but they can get really nasty really quick. So the other answer, there are so many answers to this question, but another very, very common approach, probably one of the most common approaches, is to use the numerical technique or method of gradient descent or ascent. Descent or ascent. Alright, so what do I mean by gradient ascent or descent? Well, basically, if you think of, let's do a two-dimensional example. So let's say we have a plate here. Give it some physical significance, okay? And it has some temperature profile with a max in the middle. Okay, so let's say there's a maximum here due to some heat source. Okay, and then we could draw contour lines of constant temperature around this plate. Alright, so the max here, I'm going to just draw this in red, and then as we go out it'll get cooler and cooler, so maybe this line here, slightly less red line to represent less temperature. Temperature is cooler, and then maybe a yellow curve here represent even cooler. Okay, I'm drawing contour line. We call these contour lines, and then even cooler as we go out. Okay. All right. So this is this profile, temperature profile, could be a parabolic equation. So it could be something like, I don't know, let's see, f of x, y is equal to, if this was, say, this was y, and this was x, and x and y are measured in centimeters or something like that. And so let's just say this was 10 centimeters, okay, or 10 inches, whatever we want, 10 inches, okay, and it's square. Then we could say the temperature, this is temperature, equals f of xy is approximately equal to x minus 5 squared. Let's do this minus x minus 5 squared minus y minus 5 squared minus y minus 5 squared, and then let's plus the maximum temperature. Let's just say it's, well, I don't know, plus whatever it's going to be, 100 degrees Celsius. Okay. Alright, so now we want to find the max. Well, we can use this technique of gradient descent or ascent. So because we're finding the max, we want to ascend up this hill. So this point right here is kind of at the bottom of the hill, and then the max is at the top of the hill. Okay, so this kind of looks like some kind of bowl, some kind of hill like this. Okay. Sorry, that's a pretty terrible hill. And at the edge of the plate, we're down here on the side of the hill. So we want to walk up the hill to get to the max. So with gradient descent and typically all numerical techniques, you have to have some starting point. So let's say we start here. Okay, so this right here we'll say is our vector. We'll call it r equals x naught y naught. Okay. That's our starting place. And so what gradient descent says is, okay, let's actually evaluate the gradient at this point. So take the gradient of f, which remember that is some vector, which is the partial of f with respect to x and the partial of f with respect to y. So I could calculate those values using this function. The partial of f with respect to x is just equal to minus 2 times x minus 5, and then the partial of f with respect to y is equal to minus 2 times y minus 5. Alright, so I can now, that's what these values are, right? So there we've got the partial of f with respect to x and the partial of f with respect to y. So I can evaluate the gradient. So I can take the gradient and evaluate it at r equals r naught, which I'm saying r naught is equal to x naught y naught. Okay, so I haven't put in numbers here, but if I do that, I'm going to get a vector. Okay, minus 2 times x naught minus 5, and then minus 2 times y naught minus 5. And you can imagine if I put in actual numbers here, this would be a vector. And that vector just so happens, the gradient is always going to point orthogonal to the contour line. So imagine this is the contour line. It's going to point orthogonal to that contour line, and it's going to point in the direction of steepest descent if you're starting at this point. So you see this vector points uphill. So all we need to do is take some finite step in this direction, the direction of the gradient, and we'll be going uphill. So we could do that. We could say, let's say our first guess was r naught equals x naught y naught. Okay. Well, then we could say r1, our next guess, is going to be equal to r naught plus some step size h. This is a vector. Well, no, it's not a vector, it's a scalar. H times the gradient of f evaluated at r equals r naught. So literally this is just going to say, oh, come on, pen's freaking out here. Alright, there we go. This is going to be equal to, we can think of this as matrices or vectors, x naught, y naught, plus h times what was the gradient of f evaluated at x naught, y naught? Well, minus 2 times x naught minus 5, and then minus 2 times y naught minus 5, and that becomes our R1 point. So depending on how big this is, depends on how far we step in the direction of the gradient. So maybe h is equal to 1, or h is equal to 0.5. Okay. So back up to our picture here. We're going to step in this direction, a distance h, and this will be our new guess. Then we're going to plug in our new guess into the gradient, get a new vector that points in the direction of normal to the contour lines or uphill, and take a step in that direction. And then we're just going to keep doing that over and over again until we get to the max. Now I've drawn the arrows kind of getting smaller and smaller here. That's because if I use h is a constant value, so just some constant like 1, well, what's happening to the gradients as we get closer and closer to a max or a min? Well, they should be getting smaller and smaller. So this should be getting smaller and this should be getting smaller, assuming we have some max and not a saddle point there. Okay, if it's a saddle point, then maybe only one of these derivatives is equal to 0 at that point. Anyways, but if that's the case, then the derivatives are getting smaller and smaller, so you're actually going to be taking smaller and smaller steps the closer you get to the max or the min. Anyways, and you can see that here because this x naught and y naught is going to be getting closer and closer to 5, so this number is actually going to be getting smaller and smaller. So get smaller as x goes to 5, which is where the max is at. Alright, so that's the basic idea of gradient ascent. Now, if you wanted to find a min instead of a max, you could just, instead of when you're new, your Ri plus 1 is going to be equal to Ri. Instead of doing plus h times the gradient of f evaluated at Ri, you just do, so this is, oh man, I'm having trouble writing here. This is gradient ascent, and then gradient descent, you just do Ri plus 1 equals Ri minus h times the gradient of f evaluated at Ri. Or you could just take the negative of the function, flip it around so max becomes mins, and then just find a max using gradient ascent. Lots of different ways to skin this cat. Now, gradient ascent, descent, there's all kinds of different variations of it. So there are many variations to gradient descent. I'm just going to call it descent. And there's also many other optimization techniques besides gradient methods. Optimization is its own field of mathematics and there are people who just purely study optimization methods. It's a huge field, so please don't feel like this video is comprehensive in any way. It's just an introduction. Now maybe in another video I'll actually do an example showing you how this works in MATLAB or by hand. Might be useful, but I think for now that's all I'm going to cover in this video.